Thanks, everybody. Now I think if you haven't had a chance already, it's a good time to get this QR code, or I've put a little link here, bit.ly 432v1 capital Z capital P. Because at the end, after this lecture, Karen and Laura and I are happy to do a little bit of live demos, Q&A, whatever you would like. But we would really
Natasha,
like
sorry.
Yeah,
Can you put in the chat the link as well? So that
sure.
is easier for everybody
Maybe
to.
Laura or Karen, could you do that? So I don't have to completely unshare all my
Yeah,
slides.
sorry.
That's great. Just message them if they don't respond. Yeah, so if you
The
have a look at that,
possibility.
and then we can kind of tailor the content a little bit, gives Laura and Karen at least some time to get some materials up. All right. So while you're having a look at that, I will just introduce myself. So I'm Natasha Hurley-Walker. I work at Curtin University and the International Centre for Radio Astronomy Research in Perth, Western Australia. And I volunteered to do this last part of the lecture, which will all be about radio tools and techniques. And of course, if I tried to compress all of radio astronomy data reduction into a single 40-minute lecture, it would be basically impossible. So what I'm going to try and do in this talk is bridge between quasi-reduced data products, as Laura said, science-ready data products, so you can get a beautiful image. But then what do you do with it? How do you actually interrogate that image? What do the values in that image mean? And what are some common ways of interpreting and misinterpreting radio data? For actual transformation of raw visibility data all the way up to images, that's a whole 2-day, school. And at the end, I'll put a whole bunch of reading and things that you can look into if you're interested in doing that. But this is more kind of midway through the process. Okay, so one of the things I just wanted to start with, because I think it's helps us introduce some of the fundamentals, is the units of radio. And actually this unit, the Jansky, has started to be used in lots of other fields as well, which I think is great because it is actually a unit that makes a lot of sense. So it's an incident power per spectral energy unit, so per hertz. And so this is very important that it's not flux. So flux would just be watts per meter square, but we have this per hertz because all sources have some kind of spectrum. Now you in optical are very familiar with very complicated galaxy SEDs, and in X-ray you have like thermal and non-thermal spectra. In radio, most of our spectra tend to look like this on a log plot. As Karen explained, our most common radiation that we look at is synchrotron radiation, which has a very boring spectrum until you get to the self-absorbed part, which is at the low frequency end. But there are lots of other sources that have lots of other spectra, and Karen introduced those. This is just a kind of toy diagram that we'll continue to return to throughout the talk. So when you talk to a radio astronomer, they'll often talk about Jansky's per beam. And this is really deeply weird. Like, what is the beam? I'm going to talk about beams so much in this talk. There are two kinds of beam. I'm going to cover them one at a time. The beam that's being referred to here is essentially the resolution of the instrument. It's a 2D Gaussian volume that characterizes the resolution, typically of the interferometer, but also potentially of a single dish. And so when we say Jansky's per beam, we're saying how much power in a given spectral frequency range are we getting in from that unit of the sky? So it's a brightness. We sometimes also use Kelvin. There's a conversion between the two units, but that's a little bit less common. So all radio astronomy maps are in units of Jansky's per beam. In infrared, I understand that they tend to use Jansky's per steradian. It's completely the same thing. It's just that for radio maps, we will have a resolution, and that resolution is kind of encoded throughout the map, as you'll see through lots of examples here. And so it's more convenient for us to express it as per unit resolution. It's like per pixel. It's just that our pixels are Gaussian beams. So here's an example. This is the 408 megahertz Haslam map that was formed from two single dish instruments in both the northern and southern hemisphere, at roughly similar resolutions, same frequency. And they did this very long scan of the entire sky and measured the brightness at every radio astronomy pixel, which is this beam shape. And so you can see all of the sources have this kind of characteristic size, which is 56 arc minutes in the case of this particular map. And this equation up here, theta equals lambda over d, I'm going to constantly return to. That's your touchstone for radio astronomy. The resolution, approximate resolution, is your wavelength of observing divided by d, where in this case, for this single dish map, it's the dish diameter. And so you put all the numbers together, you get about a degree in this case. So you can sort of immediately see from that equation, if we go to shorter wavelengths or higher frequencies, we get more resolution. And now how do we get more resolution? Well, we can build interferometers. So this is an image from a paper that I wrote 10 years ago now. Well, that's terrifying. And this is some very early data from the MWA, where we discovered a remnant radio galaxy around a spiral galaxy. And you'll often see radio maps where there's this little ellipse at the bottom left, and that is our synthesized beam. So it's like the equivalent for an interferometer, where instead of having a big dish where we've put all the signal together to make one pixel, we've split up the dish, we put it in different places, and now we've got to synthesize our resolution. And so we still have a resolution, but it's defined, this time the D is basically defined by the longer spaceline, which is the furthest separated pair of antennas. So you can see that all of the sources in this image all basically are the same size because they're unresolved. They're probably very interesting if you had much more resolution. We don't have that resolution, so they all look like basically the same size kind of blobs. And so this map, as you can see here, I've correctly put this in Janskis per beam. So when we want to do something with an image, we often, as I've said earlier, and Karen mentioned in her talk, we want to get that radio spectral index. That's not entirely straightforward if you have some images, right? You have them at different frequencies. And I'm going to talk you through some of the common problems that we run into when we try and do this. To show why we would want to do this, I have just show you a bit of radio physics. So this is a galaxy cluster, which of course is wonderful to look at in the X-rays as well, where you have all the thermal emission in the middle here. A shockwave has smashed through the galaxy cluster and it's left these radio shocks at the top left and bottom right. They potentially faded out and then got re-accelerated by some new electrons. You can look at the whole history of these clusters if you go and have a look at this paper. But what we're seeing here in this top shock is quite interesting, where the radio spectral index varies as a function of position across the shock. And so it's steeper here, which means the electrons are older and there's fewer high energy electrons, and it's flatter here, which means it's younger and there's more recent energy injection. That sort of history can only be reconstructed if you have the spectral index. So you actually need to get this for a lot of different objects. It's a very, very common image-based analysis to do. But I've just said that the radio brightness changes as a function of resolution, and that itself changes as a function of frequency. So if you try and do spectral index mapping without taking this into account, you're going to be in trouble. So actually, I should put a link to this in the slides at the end. I've used the Python-friendly virtual interferometer, virtual radio interferometer, to do some simulations here. It's a really handy little tool, so I'll link that at the end, or maybe I can show it in a demo. And I've just made a radio galaxy and I've run it through a interferometer. And now we have 500 megahertz, this picture of a radio galaxy. If you add up all of the flux density here, you have 1,000 Janskis of flux density. But if you just look at a given pixel, any given pixel or any given resolution element, you get like this number here. This is kind of made up. So on our toy diagram, fine, these line up on the line. But if we were to just keep measuring the brightness of a given pixel, it would appear to drop a lot faster than the true spectral index of the source, which you could get from adding up all of the flux density together. So if you were to make a spectral index map just out of this raw data, you would find that the whole source has this mysteriously steep spectrum that doesn't really agree with real physics. So what we can do is we can convolve all of the data by that lowest resolution. And basically then we won't get all of the beautiful details. You can see now that all of this data has been convolved down to the same resolution. So it all looks blobby and terrible, but any given brightness will have the same correct value, because your beam is basically the same size across the whole map. Your resolution is the same. So this is very common when you're making spectral index maps. If you rely on like distinguishing some thin filament or some kind of critical structure, then you need to make sure that your lowest resolution is good enough to resolve that structure. Otherwise, if only your highest resolution, highest frequency images, when you have to convolve them all together, you're going to lose that information. So this is constantly thinking about the relationship between frequency and spatial scale when you're doing interferometry. So once you've done that, you can just do a basic power law fit through every single pixel and you get a spectral index map. So here's a classic example where we have a radio galaxy. There's some galaxy in the middle here. It's produced these jets. The jets are slamming into the intergalactic medium at these hotspots, which therefore have a flat spectrum, and all this backflow has a steep spectrum. So this is, again, just coming back to the sort of physics you can get out. There's a fun thing just to sort of tie into Laura's talk. When you are doing radio observing, some interferometers have different configurations that you can request. So the Very Large Array in New Mexico has 4 configurations, A, B, C, and D, where A, the antennas are furthest apart, B, they're a bit closer, C, closer still, and D, they're very compact. You can see I've got B and C written here. So B, it's sort of like 8 kilometers end to end, whereas C, it's like 2 kilometers end to end. That means that if you observe at a medium frequency in your long baseline configuration and then a high frequency in your shorter baseline configuration, you can actually match the spatial scale sensitivity. So this is kind of an old school way of ending up with the same images. And here, this radio galaxy, it looks like it's the same image. If you actually had access to the slides, which of course we'll share at the end, if you zoom right in, you can actually see these are different, and that's because they are simulated with slightly different UV coverages. And I've actually used this in order to do radio galaxy imaging. Hopefully in the era of the SKA, we'll just have such a surfeit of just so many baselines. We won't have to worry about UV coverage. We'll just get beautiful images no matter what we do. But we're still in the pre-SKA era, so we have to think about this stuff. Okay, so that's all very good. I've talked a bit about matching resolutions, trying to get that fine scale information, trying to get the spectral indices of individual features. But there's a very important thing we need to think about here. We've talked about your longest baseline. That's where we get the resolution. But the shortest baseline is also really important. And this is something that even radio astronomers who've been working for decades will still get wrong about their maps. And I've been going to illustrate it here with an example from the GLEAM and GLEAM-X survey. So your shortest baseline dictates your maximum angular sensitivity. So GLEAM, we performed with the MWA in its first configuration, which was 128 tiles, and the closest those tiles were together was basically right next to each other. Between 2 tiles was sort of 2 to 3 meters. They were absolutely almost touching. There's such a short baseline. At 150 megahertz, nearly touching is basically a scale of 10 to 15 degrees. So you're really picking up very large structures on the sky. GLEAM-X was performed with a reconfiguration of the MWA where we did not have any short baselines. And the shortest baseline was about 100 meters. And that means that even at a scale of 20 arc minutes, you're starting to lose flux density. You're no longer actually correctly sampling the object in the first place. So when we go through complicated processing to turn those raw data into images, when we can reconstruct the images, that scale is simply not present. So you can see this beautiful image of the Baylor supernova remnant on the left. If we use GLEAM data, it's low resolution, but you get all of the spatial scales that are relevant to the Baylor supernova remnant, a few degrees. But on GLEAM-X, we get a bit of resolution. You can see all these beautiful filaments, cannot actually see the whole power of the remnant. So this is just really important because it means if you are interested in the brightness or flux density of an extended object, you cannot reconstruct what isn't there. You can convolve it down to lower and lower resolutions, but you will not be able to reconstruct it. Laura mentioned that the total power is only accessible to single dish telescopes. That's basically a baseline length of 0. Right, the actual power on the sky is completely lost for interferometers. They can only see differences. So this is a subtle point, but if you care about extended objects, you have to worry about it. Okay, another fun thing to worry about with radio telescopes. Coming back to our theta equals lambda over d, I did promise you I would tell you about more than one beam. So the resolution comes from synthesizing all of our different elements together to produce this virtual resolution element. But each tile or dish has a sensitivity function itself, and that is called the primary beam. So that typically for any given instrument will have some main lobe that is particularly sensitive to the sky, and we often call that the main beam. Sometimes we just call that the primary beam itself, even though it's really just one lobe of it. And then it will have these side lobes, and that is just a consequence of engineering. It's very, very, very hard to make a perfectly directional antenna. You're always going to be sensitive just on a little bit of a scale to things coming from the outside. And so it's in dishes, that's often called spillover, where you have radio waves coming from areas that you really don't want to actually be sensitive to. For things like the MWA, which is fixed on the ground, side lobes are part of the primary beam, and that is just how it is. We just see a bunch of stuff in varying sensitivity across the sky. Now, if you are using data that has come out of a survey, this effect will absolutely have been taken into account. People spend a long time fixing the primary beams, like you have to measure them. Sometimes people use drones, sometimes people use holography. They measure the sun. It takes a lot of work. But we really don't want to have to expose non-expert users to primary beams. We really would rather get rid of them. So, well, any survey that you need to use, largely these effects will have been taken into account. So, as I say, the field of view will vary depending on the theta equals lambda over d again. So this time d is the size of your station or the size of your dish, and this is, believe it or not, the same part of the sky as seen by the MWA and as seen by Meerkat, and I have locked them in DS9. And you can see what effect you have by building a small size station and observing at low frequencies. We see the whole sky practically, and use a big dish at high frequencies, you see a very, very small amount of the sky. And so when we correct for these effects, this is a corrected map from the MWA, and you can see that the noise goes up very steeply at the edges, as opposed to in this image, the noise doesn't appear to be going up at the edges, but you'll also see there's no sources at the edges. And that's because we actually are losing sensitivity. The primary beam is attenuating the flux densities of all of our sources. So if you tried to use this for cosmology or something, you'd say there's something very strange happening with the sky. But we try and correct for that, but that of course means all the noise goes up as well. So if you're looking at individual snapshots, if you download some images from CASDA, from ASGAP, if you have suffered through some radio astronomy to data reduction, and then you've divided through your primary beam, you'll have this uneven sensitivity. And like I say, with a survey, we always try to take lots and lots of observations and get rid of these areas of low sensitivity. Another note is that, again, theta equals lambda over d. So that means that this whole thing is frequency dependent. So if you have, for instance, used the wrong primary beam, or you haven't primary beam corrected, then for any source that is not directly right in the middle of the main lobe, you will have some kind of artificial spectral index that is not correct. So these has to be corrected properly in order to get a real flux density. Okay, so that's kind of the nightmare of dealing with images, but hopefully most images that you download, like if you get them from Skyview, you get them from CASDA, those effects will be taken out. And note them because it's important to understand, what's happened to your images and what has already been done. Now, images are very pretty. If you have some extended object, you want to see if something is simply there or not, they're fine. But I did a lot of extragalactic radio astronomy and cosmology for parts of my career. And in those cases, we want big samples, typically, of radio galaxies, so that we can go off and look into the universe. Trying to do that with an image makes absolutely no sense. So we want to turn our image into a catalog rather than trying to do something with the image. And I was thinking about this, I was wondering whether it was too basic, and then I thought, wait a minute, when I look at an X-ray image, I have no idea how you guys decide that's a source, that's not a source. You've just got like a cluster of photons. That seems very painful. This is just as painful, but in a different way. So I think it's worth explaining. So there are actually a lot of different radio source finders. I put on the right-hand side here a plot of how Aegean works, which is one of our most commonly used radio source finders. You don't have to go through all of the detail here. The main thing I just wanted to draw out was that typically, because of our resolution, we know that the sources are essentially no smaller than that synthesized beam. And the synthesized beam itself is a 2D Gaussian. We tend to represent all of our sources as a collection of 2D Gaussians, typically like 1 or 2 or 3. So that's kind of like the back end foundational assumption in a lot of radio source finding. So I did some quick little Python examples of what source fitting would look like in a perfect universe, and then I'm going to make it steadily less perfect. So here we have a hypothetical Gaussian source in a 1D image. All of the instrumental effects have been taken out. There's no noise. Great. This is very easy. We just fit a 1D Gaussian. In the header of your fits image, there will be some values called Bmag, the major axis, Bmin, the minor axis, and Bpa, the position angle of that 2D Gaussian that describes the PSF. And as a note, that's the full width half max, not the standard deviation of the Gaussian. And so any source finder will just read those in, have a look at that and go, oh, it's exactly the same. I'm just going to fit a 1D Gaussian to it, well, a 2D Gaussian. And if everything is working well, then an unresolved source will have exactly the same dimensions as the PSF. Another way of putting this is that the total flux density, the integrated flux density divided by the peak will be 1. So this is kind of a nice check that we often do to make sure that our source finding is working properly. We look at some unresolved sources and we say, are these numbers, is this ratio 1? Often there's going to be some background. So this is a little chunk of that MWA image I showed you earlier. The MWA has those short baselines. It sees those big spatial scales. There's a lot of diffuse galactic synchrotron all over the sky. And you can see that this causes this big positive and like negative striping and a sort of slowly varying background. That's real signal. It's just very poorly sampled real signal. And so effectively to our source finding, it forms a background that we don't really want to include. We would rather get rid of that. So we have some nice algorithms that can step through this kind of data and measure the background. Aegean comes with one called the background and noise estimator. I've represented it here as everything is offset by 50 millijanskis. And that's relatively easy to see in this example. There's also going to be noise. And again, like notice in this image how the noise itself is also no smaller than the scale of the synthesized beam, the point spread function. We are always fundamentally insensitive to anything smaller than that. So the noise itself is varying on this same kind of time scale, spatial scale dictated by the longest baseline. So here's some representative noise. And so your source finder will do a job. It'll go through this and it will attempt to, using various different algorithms, separate out your source from the background and from the noise and retrieve one 2D Gaussian. Now, of course, a single 2D Gaussian is not a good fit. If you imagine some of those beautiful things I showed you, like Radio Relic, that galaxy, the remnant radio galaxy, none of those look like 2D Gaussians because they're sufficiently extended. So source finders will also provide a flood-filled region. They'll typically like flood fill out to like 1 sigma or 2 sigma, 1 times or 2 times the RMS value of your map, and give you that. And then you can take that and add up all the flux density inside of it and go and do things with it. That is going to get complicated in maps like this, because where do you decide, is this sort of grouping here a source, several sources? It's very hard to tell. At the end of the day, you'll end up with a catalog. I've just booted this very quickly up in Topcat. It's just one I had lying around. We try to provide a lot of information. I mean, we're no Gaia, but every radio image we try to give you as much information as you would need to reasonably interrogate the data. So this is just a bunch of 2D Gaussians. I've colored the map by the local root mean squared noise. So you can see this, since this has been primary beam corrected, it's lower in the middle and bigger at the edges. You get all these other informations like the sizes of the sources and where they are and how bright they are and useful things like that. That all makes sense for individual sources, and for radio galaxy and cosmology people, that's often sufficient. But if you're working in the galactic plane in areas of very, very, very complicated emission, there's not actually like an off-the-shelf solution for this. So if you're in this situation, I have written some software myself. I have to say I would love to spend more time polishing it and making it more generally accessible, but it works well enough. So here is an image of some MWA data at 200 megahertz, and this is 3 other frequency channels, and you can see that this is kind of tying into what Karen was talking about with radio astrophysics. We have some areas with thermal spectra, where they're brighter at the high frequencies, which is why they're blue, and we have some areas with synchrotron spectra, which is brighter at the low frequencies, and so they appear orange. I'm particularly interested in this new supernova remnant I discovered, so I've written some software where you can draw a box around the supernova remnant, decide which areas you don't want to use for backgrounding, and then we'll add up all of the flux density and subtract the average background or a 2D plane for you. And then this is what you get out at the end is, here's your flux density against frequency, and look, we're retrieving the power law spectral index of the supernova remnant, which is what we wanted to do. I feel very bad recommending this software, but if anybody, because it's just hacked together, you know, I'm not a software developer. If anyone has any better recommendations for radio aperture photometry, then let me know. So I've talked a little bit about noise. You don't want noise. No one wants noise. We would like to reduce our noise as much as possible. How can we do that? Well, there is a convenient equation, the radiometer equation, which I have simplified right down here into just the main terms that you should care about for the purposes of this talk. You have a total temperature of everything from the sky all the way to your telescope and all of its electronics, and divide that by the square root of the bandwidth and the integration time. And so, of course, if you have a wider bandwidth, that's great. That's going to lower your noise. Modulo, if you're observing over a wider bandwidth, your primary beam gets very strange because it's narrow at the top and wide at the bottom end of the band. That's going to be a big problem with SK low. So there's some kind of limit over which you're no longer even seeing the same sources with the different parts of your band. More integration time, sure, that's better. What if you're observing a transient radio source? That's going to be limiting you then. You really can't integrate over something that's varied because you're going to get nonsense. So you're kind of limited at some level, or possibly your source rises and then it sets and you have to come back and go over and over again. And this total system temperature. And if you've ever wondered why the MWA is just a pile of metal in a field, why don't we have those fancy helium-cooled receivers? Well, it's because the sky temperature is so high that the system temperature here on Earth is essentially completely negligible. So this non-thermal synchrotron is so bright, it appears to be hot to our radio telescopes, and it's just so incredibly bright at low frequencies that is by far the dominant impact on the total system temperature. Once you get to 1 gigahertz, this becomes a lot fainter, and then the system electronics and the receivers and everything start to become the dominant source of noise, and then you get all the way up to, you know, ALMA, South Pole Telescope, tens to hundreds of gigahertz, and you're talking hydrogen, helium, nitrogen cooling. Just a fun kind of fact, basically, like touching on what Laura was saying about measuring radio waves with a piece of wire. If you get a directional antenna and you point it at the galactic center, if you have a Raspberry Pi on it that's telling you what the temperature is when you're in the thermal regime, you're bringing your antenna to the temperature of the sky, which I really love. It's just by pointing it in different places. I could get into a whole thing about brightness, temperature, antenna temperature. We don't have time. All right, so of course, if you're trying to get some really deep measurement, get a better bandwidth, look for more integration time, get a nice sensitive telescope, those are top things that you can manage. You will eventually hit limits. So we have confusion noise in radio. And if anybody here works in infrared, you'll be pretty familiar with this, I would have thought. This is the effect where, because our resolution is sometimes quite poor, there'll actually be multiple sources. Well, there's always multiple sources, but they become bright enough the more you integrate, that they completely fill your synthesized beam, and you simply cannot go deeper than you have gone. So as an example, I have a bit of a cutout from EMU, which is a big survey being run by ASCAP, 10 hours of integration time. At 10 arcsecond resolution, it's native resolution. If you look at the character of this noise in between the sources, it looks quite Gaussian. It looks like white noise, static noise, except perhaps around the bright sources, and these are calibration artifacts, which I will not have time to go into, but they're slightly non-Gaussian. But you could keep adding to this, essentially, because the noise is quite Gaussian. You could do another 10 hours integration and you would still be able to get a little bit deeper. However, if you convolve this to a lower resolution, so here it is convolved to 45 arcseconds, now the background noise actually looks like background, right? It doesn't look like noise anymore. It actually just looks like a sea of unresolved sources. If you study the cosmic infrared background, that's essentially what you see. It's just this huge susurrus of unresolved sources that goes on forever. The effect of that is that if you are trying to make some observations and you have some signal to noise and you keep adding more and more observations into your image, you're going to hit a floor. And then the only solution to that is to go to higher resolution to disentangle all of the sources and avoid the confusion. That's hard because you have to build longer baselines. There's a subtle additional thing which I'll cover, but I appreciate it's quite technical, called side lobe confusion. My analogy for this in the optical is if you imagine you have a telescope that has very bad diffraction grating patterns around lots of objects. Well, that's an interferometer. We have terrible diffraction patterns around every object, essentially. And a whole part of our cleaning, our data reduction process is to clean these synthesized beam side lobes out of the image so that they don't bother you. However, that process is limited. It's not perfect. And so it does a lot better if you can integrate for a long time. Then you will remove this effect a bit more. But if you integrate for short times, as Laura was mentioning earlier, then this effect becomes very large. Essentially, we're not completely sampling the sky. So the image at the top here is formed of lots of individual MWA images where we've done our best, but a single integration was not enough to clean out all of these side lobes. And so you can see all the individual sources have these sort of negative bowls around them, and that's kind of this side lobe confusion. So that's what's dominating our noise here. Okay, so I'm really at the tail end here. Once we've got a catalog, or perhaps you have gone into some extended image of your source and you've used some aperture photometry, or you've run some source finding and you've got a flood fill. Now you've got some data from some different surveys at different frequencies. Okay, well, what do you do with it then? How do we actually go from that to some physics? Typically in the past, radio surveys have been quite limited. There really has been a huge explosion in the last 10 years. And so we would just have like a point at 1.4 gigahertz and a point at 8 gigahertz or something, and we would fit a line between them and we would say, well done, everybody. We've done a great job. But now with these wideband receivers and so many more instruments and surveys, we're getting lots and lots and lots of points to fill in our radio spectral energy distributions. And so spectral fitting has actually become quite a bit more interesting in the last few years. So this sort of thing that I would typically do is define a model, and that could be my very basic power law model. It could be a curved spectrum model, and then I would just use SciPy to do the fitting. I can show you some code, I suppose. You could also define a physically motivated model. So this is synchrotron self-absorption, where basically you have a turnover as the object becomes synchrotron self-absorbed. And then you could just fit this to your data. And as long as it's standard statistics, right? As long as you've got more data than you have parameters in your model, then you will get a fit. Pretty much at the point where you start to be fitting like doing complicated physical fits, you might want to check out some of the packages that exist for doing this. This sort of depends on your science case, how they've been set up. For big catalogs of radio galaxies, I'd recommend Radio-SE-DE. For doing spectral index mapping of extended sources, I would look at Harwood et al., Bratz. Just recently, Nick Swainston did a fabulous job at putting together all of the pulsar data across all frequencies. So he's got a package called Pulsar Spectra that will do these fits. And there's also a nice package, which I only learned about recently, which if you have a supernova remnant or some other high energy thing that will produce gamma rays, you can jointly fit synchrotron produced by the remnant in radio and with gamma rays at the same time. And there's probably even more, so please do put them in chat if you have other suggestions. And then from these non-physical fits, you get some numbers which you can report. From the physical fits, you can actually then go and take those and do things like calculate the magnetic field or you know, the energy density or whatever your physical fit depends on. So here is a enormous number of links, which of course I'm happy to share the slides. I guess I want to break this chapter of a book that I wrote, which kind of has a similar tone to this lecture, where I don't assume that you actually know anything about radio astronomy to start with. So that's freely available online. This kind of gets steadily more technical as you go down. And if you really do want to reduce radio data yourself, Laura, Karen, and I, and a whole bunch of other wonderful people organized and spoke at a radio school last year, where we spent an entire week teaching students how to do this from scratch. So you can check out those recordings. We have all the slides and recordings up on that website. Otherwise, as always, just talk to a radio astronomer and we'll try and help you out. So if you haven't yet filled in the survey and you do have strong opinions about what you would like to do next, please do that. Otherwise, I will take